welcome to the lecture of this finite volume method. So, now we will move to the second part of it, this is the discretization process. So, once you go there, then we will look at the discretization process. Now, what we talk in the discretization process? So, essentially in the discretization process, we will be talking on modeling of the geometric domain and the physical problem of interest. That essentially again coming back to your calculation of the CFD related work, that when you have a problem in hand, how do you convert them to the mathematical problem or the linear system and finally get the solution. So, there we will be discussing the geometric domain and physical domain. So, one is the geometric domain is the physical problem that it will represent, and the physical phenomena of interest, that means it could be flow through channel, it could be flow around your automobile vehicle, it could be flow through ventilational duct, anything. So, one case it is has a bifurcation of geometric domain and then the physical problem. Then you need to discretize the geometric domain into grid or mesh. So, this is one very important point. That means, once I have a geometric domain in hand, so I need to make them in finite number of grid, or we sometimes call it a mesh. So, over which we will have the solution. Then you actually discretize the numerical equation to get a linear system. So, this is where your physical problem of interest through the mathematical technique getting transferred to a linear system. Once you get transferred to a linear system, you get a solution of the linear system. So, essentially this is the solution that you are looking for of a linear system. So, in the discretization process, we will see how a physical problem is transferred to a linear system. Now, if you look at the problem, so essentially one hand you have this physical problem and this is the physical phenomena. So, once you have a physical problem in hand, so the physical problem does not come without a physical phenomena. So, that means if I have a flow through a channel, the physical domain is the channel and the physical phenomena is the flow which is going through that channel. Now, this is physical domain will have a domain modeling and the physical phenomena will have a physical modeling. So, physical modeling means essentially you are going to have the set of governing equations or the physical equations that will actually represent this physical process. Okay. So, this will actually take care of the governing equations. Now, that will lead to a set of governing equations defined on the computational domain or computational grid or mesh, whatever you call it. So, essentially the physical problem now getting transferred to a computational system. Now, you have again two set of system. One hand you need to discretize the domain, this is called the domain discretization. That means, if I have a channel like this, so I have to discretize this one, and the domain discretizations will lead to a different kind of grid, and that we have already talked in our previous lectures, that what kind of grid you end up with. It could be structure grid, it could be block structure grid, it could be unstructured grid, and then you have a governing equations which actually you discretize through different schemes. Okay. Then you get to the linear system, which is Ax equals to b, and then finally you have a different solution method. So, solution method could be multiple, because how I can solve this linear system, it could be direct solver or it could be linear solver, a iterative solver. So, it could be iterative solver. Then once you get the numerical solution, that will actually represent your physical phenomena. Okay. So, this is how you get the system going. Now, you haven't taken example and see how things actually move on. So, here is a base of heat spreader. This portion is the heat sink and this is a another patch there. So, it is essentially a microprocessor. Now, if you look at the domain modeling, so domain modeling if you look at it, so this is the how you look the domain modeling. This is my microprocessor, this is my heat sink and this is the heat spreader base. Essentially the heat spreader base is a kind of an L-shaped base where I have a heat sink, where I have a microprocessor. What does my physical modeling do? Physical modeling essentially talks about my governing equations or the equations that represents the phenomena. So, physical modeling essentially does that. That means I come up with the equation which can represent this physical process. So, if you look at this heat spreader base, one hand I have a sink, that means it is going to be the energy absorber, then I have a microprocessor which might be generating the heat. So, I will be essentially solving a steady state heat conduction equation with a heat generation term. Why there is a heat generation term? Because the microprocessor sitting in this heat spreader base, it is going to be, so this is going to be the heat generator and this is going to be the heat sink. So, both the condition is there, so I have to solve that. Now, when you come down to the domain discretizations, how do you discretize these things? So, the spreader base is discretized with some sort of a finite elements or the some structured elements or control volumes. So, these are individual control volume. So, you define them in a regular control volume and this is a patch. This patch is nothing but my heat sink and this is patch 3 which is the microprocessor, this would be heat source. Okay. Now, equation discretizations, I have the governing equations with source term. So, I have an unsteady term and convection term, diffusion term, this term, but in this case it is a steady state case. So, that I do not have any contribution from this term. So, finally, it comes down to some sort of a, this is a algebraic equation. Okay. And if you look at that, this would be put together in this kind of a matrix form and this is in a particular one control volume which can represent through this kind of estimate. Now, if you look at the complete picture here, this is my problem of interest where I have a spreader base, I have a microprocessor which is actually heat generator, I have a heat sink, then domain discretizations actually take care of the whole domain, physical modeling actually gives back to my equations, finally domain discretizations takes into account the control volumes, then you come down to a linear system and you get a solution which will be the physical phenomena. So, that is how the whole process actually works. Now, if you look at the geometry or physical modeling. So, geometric and physical modeling, what we are doing this actually it simplifies the system, then it takes care the governing equations, that means the PDEs which represent the physical phenomena. Okay. So, that is what we do, and in this case you have a steady state heat conduction equation with a source term. This is my PDE. Okay. So, first step is the geometric and physical modeling. So, the geometric modeling, we identify heat source, we identify heat sink, we identify the other domain constants, and the physical modeling will get back to the equations. Now, the second step would be the domain discretizations. How do you do the domain discretizations? Now, the second step is very important in the sense how you look at the system or you discretize the domain. So, this is my complete spreader base. This is a L shape base. This portion is the heat sink. So, I have a boundary condition of T sink. This is the heat generator of the microprocessor. So, there is a boundary condition of the microprocessor. Then the outside is insulated. That means no heat is going out. So, this is stopped. There is no heat flux. So, that is 0. So, this is the domain that I have to discretize. So, essentially you can think about this picture actually represent your computational domain. Okay. This will actually take care of my physical problem in hand, because this microprocessor will be the heat generator, this guy will be the heat sink, and then I have insulated base. So, that actually takes care of my computational domain. Now, the second part is the generation of the computational mass. So, this portion I have a boundary condition, at the heat source portion I have a boundary condition, then there is a boundary condition. Then if I discretize them with a structure control volume. Okay. So, this looks computational mesh. So, this is structured mesh or quadrilateral mesh, or other option, this could be option 2. So, this is one option. Other option is that still I can maintain this. These are the two patches, one is heat sink and one is the heat sink, another is the heat source. This is insulated base and I can generate unstructured grid. So, this is also one sort of computational mesh, but it is unstructured. Okay. So, in a domain decomposition step, that means in step 2 you identify the computational domain, then you generate the grid, either structured grid. If it is a geometrically it is simpler, then you can generate structured grid. If it is geometrically not simpler, then you can use unstructured grid to generate the domain. Now, if you identify them with the all sort of points. Now, if you consider that structured grid, if you consider that structured grid with the quadrilateral elements. Okay. So, these points, all nodal points in this particular computational domain, they actually represent the mesh vertices. Okay. This is my one individual computational control volume. So, this is one of my control volume, and the control volume is connected with 4 vertices. So, these are called mesh vertices, and when this control volume is connected like this, that forms the essentially the mesh. Okay. Now, second picture, if you look at it, then each of these control volume are having 4 different phases. For example, if you look at this particular control volume, now this gives you the idea about these phases. So, these are phases of control volume, and what it helps, individual control volume are connected with 4 phases, and these phases are going to be very important as we see down the line of these lectures, that we need to have the understanding of these particular phases. Okay. And finally, if we look at it, or if you mark this whole thing 1, 2, 3, 4, these are all essentially control volume or elements. where I am going to have the solution done, and this will be my boundary condition for the sink, this would be the boundary condition for the source, this is the insulated boundary. Okay. So, now I can have the mesh details. Now, mesh details, one could be the important thing is the element connectivity. Okay. So, element connectivity, if I look at this particular condition, so this is my domain and I divide into 9 element. This is C, let us say this is there, all this is F1, F2, F3, F4. Okay. So, this is around C. If you look at the neighbors, so neighbors are 10, 4, 8, 15. So, based on the numbers. Okay. So, you can have faces, these are the faces, okay, and these are the vertices. Now, one could be the phase connectivity. So, when you talk about the element connectivity, you need to keep track of the elements. That means, one particular element once you consider, you need to see what are the neighbors. Now, phase connectivity, if I just look at this situation, okay, here is a element, this is a element, these are the element. So, this is E1, let us say, this is E2, then the neighbor of E1 is E2 and the connectivity of this is the phase. So, one hand it can go, this normal of this phase goes like this. So, E1 and E2, they are connected to each other, they are neighbor, and the F is the corresponding phase. And another way you can have the vertex connectivity. Okay. So, the vertex connectivity means if I have, let us say, this 4 element system, okay, and these are there. Now, vertex connectivity would be if I connect this with these points. So, this is called the vertex connectivity of the system, and once you take them into the complete domain. So, this is my, if you look at this particular some example of 1, 2, 3, 4, 5. Now, I am interested in the element 3. Now, element 3, the equation if I discretize. So, do not worry about this discretization or the discretized equation, we will see how we get back this equation. If you look at element 3, what are the neighbors? So, neighbors are 2, 5, 1. Because why we are calling it the neighbors 2, 5, 1, not the 4? Because the element 3 and 2, they are having a common phase of F. This is the common phase. Element 3 and 1, there is a common phase. Element 5 and 6, there is a common phase. But if I look at element 3 and 4, they are connected with one common vertex, but they are connected with common phases. So, neighboring elements, these are neighboring elements, not neighboring vertex. So, you can say this is F1, if I go by that, this is F2, this is F3, that means these are the phases, and I can write down my equation for that. Okay. And if you look at in the complete system, this probably, so the equation is talking about 1, 2, 3, 4, 5. So, all the elements, the equations are written, and any somewhere between that one line will represent for the element 3. So, that means when you actually discretize the system like this and you get back to the complete, when you actually put them together, you get a system, overall linear system like this, and all these in this particular system every individual elements they are taken into consideration. Now if you go to the equation discretizations, so what is the equation? Basically I need to solve A x equals to b, and here x is nothing but my t, so I can say a t equals to b. That is what I am trying to solve. Okay. And where I am trying to solve? I am trying to solve over this particular computational domain, and these are all my individual element. This patch 2 is the T sink, this is T source, and this is Q flux is 0. Now here if you look at all these interiors points are 1, 2, 3 to 25, these are marked. Okay. Patch 1 having some points, patch 2 having certain points, patch 3. So I have to make a demarcation of these faces, because these faces I have boundary conditions. So once you make a demarcation of these faces, you actually now look at the tensile. So what equation you are going to solve here for all these points is the delta dot k delta t dV equals to q dot dV. So this is my equation, and this equation is valid inside the domain as well as at these faces, but these faces there will be boundary condition for t. So I have to apply my boundary condition to have this. Now when you look at the discretization stencil, so this is how you number the element. So basically this could be 1, this could be 2, that is how you sequentially number the elements, and once you take an individual element, around that you mark the faces. Not only the faces, what you have to mark is that the corresponding neighboring element. These elements are very important to keep track of it, because these neighboring elements are going to. So now if I write down the equation, let us say I will write down the equation for C. There is a element, this particular element, if I concentrate on that particular element. So my equation would be minus k surface delta t dot ds equals to q dot Vc. Okay. So if I do that summation, so around that C, this is k delta t dot Sf equals to q dot C Vc. Okay. And this F goes over that surface, that means 1, 2, 3, 4, these are the surface. So the summation would be over those surfaces. So if I write that k delta t of surface 1 dot Sf1 minus k delta t F2 dot Sf2 minus k delta t F3 dot Sf3 minus k delta t F4 dot Sf4 equals to q dot C Vc. So this is my, now you see my steady state heat conduction equation boils down to this mathematical expression. Now what is my Sf1? Sf1 would be delta y F1 I. Okay. So if you look at it, that particular element C, now I am dividing this in the x direction, this is small x, the uniform width, and this is delta y, then my Sf1 would be delta y F1 I, my delta x F1 would be x F1 my minus xc. So this is the distance between this, F1 is the neighboring cell on the upstream side, and delta t F1 is nothing but del t by del x F1 I plus del t by del y F1 j. Now what is xc? xc is the coordinate of element C, xf is the x coordinate of F1 element, then you have delta y F1, delta y F1 is the area of face F1 and S F1 is the surface vector of F1, and then delta T F1 is the gradient of T1. So, this is how it transformed to the system. Now, we will stop here today and then take it up in the following lecture. From here how we proceed to get that final linear system.